Thanks, Will, for the presentation. And we are going to shift a little bit from the subject of software and systems to science again, to the extragalactic domain. In particular, these low-surface brightness galaxies, or LSB galaxies, more familiar. I will try to convince you in this short talk. This is just a glimpse on this subject. I will not enter into the big technical things. It's just to show you why these galaxies are relevant to this instrument, new instrument, Argus 144, and the opportunity that they represent. So first, just to show you the large scales, spanning scales where you found these LSB galaxies. You have here the Dragonfly 44, discovered by Van Dokkum in 2015, and the MALIN 1, a big low-surface brightness galaxy, is perhaps the biggest galaxy in the universe discovered so far. So it's very important to understand this kind of objects. You can see here the enormous difference in scales of two galaxies that are pretty much of the same surface brightness, MALIN 1 and Dragonfly 44. This is impressive, right? So what are the general properties of these galaxies in general? Okay, and some pending questions that are not answered yet. First of all, a low surface brightness galaxy is a galaxy with surface brightness fainter than the average sky night brightness, which is about 22 magnitudes per square second in the B band. This is an historical origin of this, okay? It's just because of the definition of Ken Freeman when he thought that they had discovered a limit in the disk of galaxies, but that was just a bias imposed by photographic plates in the 70s, as many of you know. Okay, so this simple observational fact of have discovered some galaxies that are fainter than the average sky night pose a lot of consequences that has been studied in the last 30 years. In particular, they present low stellar formation rates. We don't know yet if that is because of lack of molecular gas or low molecular gas density. How low is not completely sure. Okay, they also have, in general, large H1 fractions, like, for example, MALIN 1. We will talk about this a little bit later. And they also have very flat, extended rotation curves, which perhaps imply, of course, that they have large fractions of dark matter. They also have high specific angular momentum, which is interesting when you separate different populations of galaxies, and this is probably related with the origin and formation of these galaxies. They also have appear relatively isolated in the cosmic web or in the outskirts of these bubbles that fill the universe. And also, but you can see, however, the discovered by Van Dokkum in 2015 of these ultra diffuse galaxies that has been remarked by Sandage in the 80s. Okay, so in this talk, I will just focus on this feature of these galaxies, which is the low stellar formation rate and the lack or low molecular gas density in particular. Okay, so why these galaxies are relevant? First of all, they dominate the volume density of galaxies in the universe. In this plot, compiled by O'Neill and Botton in 2000, you can see the dramatic relevance of these galaxies in the volume of the universe. Here you have at the right, most of the galaxies you are used to see, spirals, ellipticals, etc. And to the left, you have, in fact, all these galaxies fainter than 22, 23 in general, that really dominate the volume density. Okay, so if you want to really understand how galaxies are formed and how they fill up the universe, we have to understand this very faint end in surface brightness in the universe, and not only the brighter part of the surface brightness domain. Second, they dominate the end of the mass luminosity function of galaxies. Here you see, again, this is a luminosity function, but in terms of stellar mass, okay? And you see that all the left tail is dominated by low mass galaxies that in general are in fact low surface brightness galaxies too, okay? In this talk, on the other hand, I will talk mainly of giant LSB galaxies that are not dominating the faint end of stellar mass, although there are some examples, like for example MALIN 1, that perhaps are at this level, okay, at the level of 10 to the 8, 10 to the 7 even stellar masses. Okay, so why giant? Well, giants are always attract our attention. We can see this Gulliver picture, right? This is almost the same. We are pointing a lot of arrows into MALIN 1. Not all of them are pointed to the blank, but to the target, but we are trying. Okay, so this galaxy, MALIN 1, was discovered in 1987 by Botton and collaborators. At the beginning was really a mystery because this galaxy is in fact at 0.083 in redshift, which is not so close, okay? This is very far away when you see other LSBs, okay? So it was from the first minute a mystery because it is far away, it's very big. It's also a very age-rich galaxy. It's one of the biggest, in fact, reservoirs of H1. If you compare MALIN 1 and other giant or pseudo-giant galaxies, you can compare the size of the Milky Way with these galaxies. These are one of the biggest examples of the biggest galaxies in the universe. You have UGC 6614, UGC 1382, which are very big too, like MALIN 1. And when you compare to the Milky Way, it's really obvious that these galaxies are very interesting, right? Are big, but very diffuse. Why? What happened when they formed is not completely clear. When you see just MALIN 1, you discover also other things that are very interesting. First of all, this is an HST image by O'Neill. Karen O'Neill was one of the pioneer scientists that investigate this kind of galaxies. When you see this galaxy, you see a very boring galaxy. This is the central part of the galaxy. You have this HST image, you have a faint disk, and this is one of the, perhaps one of the reasons why MALIN 1 was not a target in the second, I mean, after 2000, because many people thought that this image, HST image, has told everything about this galaxy. There's no spiral arms, there's nothing. And so for many years, more than 20 years, nobody has targeted this galaxy again in optical images. But on the other hand, this galaxy is only 600-second exposure time. So when you point out another telescope, a big one, you discover that this galaxy is in fact a very peculiar one with very broad, thick spiral arms. And when you compare to the Milky Way, again, you see that this is a monster, right? So the spiral arms of this galaxy are very thick, as I told, and they are also 28 magnitudes per square second, so they're very, very diffuse. It's perhaps one of the galaxies with the more diffuse spiral arms we have observed so far. And also, again, the diameter is 200 kiloparsec. It's a huge, huge galaxy, okay? Well, what about the molecular gas, which is the topic of this talk? Well, the first detection of the molecular gas in giants has been very complicated to discover. The first detection, again, was Karen O'Neill with IRAM 30 meters, but not a giant one. It was a galaxy, obscure galaxy somewhere in the universe, not these big grand design spirals, okay? Then Matthews, again, in 2001, discovered, again, CO in one of these LSBs. But what it did was very difficult, again, okay? And regarding the really giant LSBs, most of them lack molecular gas, or the gas was still not discovered in many of these galaxies. MALIN 2, for example, present a faint emission that was made by Mosumi Das in 2006, and was very hard to discover this emission too. Recurrent failures has been the usual aspect of MALIN 1 molecular gas. Many people has pointed a radio telescope to MALIN 1 without success. That includes Karen O'Neill, Brain, Mosumi Das, and others. Patricia Nesek at the early 90s also tried to discover gas in this molecular gas in this galaxy without success. So most of them have low metallicity that perhaps is by the hand with low dust, Perhaps that is implying weak UV emission, or weak UV shielding, and also perhaps that implies a higher temperature of the CO. But there are other opinions on this. For example, Brain, using IRAM 30 meters in 2000, point many places in this galaxy, which also we target with other collaborators recently, and they didn't discover any trace of CO. You can see in this right in this emission plot. Okay, so no detection up to the level of 2 millikelvin, okay, per channel, and neither in 1L and 2.1 in CO. Okay, that was one of the last efforts to discover to detect CO in this galaxy. So
3-minute warning,
we are talking about, thanks, 20 years ago. Okay, why few detections is not completely clear, but of course the fact that the galaxy is devoid of dust have an important role of this. Okay, we think that the dust is some sort of shielding of the UV radiation, and so perhaps the gas is a hotter temperature than expected. Perhaps it's also a good idea to point radio telescope to detect diffuse gas, for example, carbon-1 and others. This is important because these galaxies are at the end of the Krumholtz diagrams when you have very low gas density, okay, and a very low stellar formation rates, very low efficiencies. So these galaxies, LSBs, are at the end of this sequence, and very few have detected gas in this. In particular, wider have done a little bit of this job. Okay, so in the last year, with Dave Fryer, we are trying to detect molecular gas with the GBT using Argus. This is the map where we have been pointing the telescope, and the news is that no detection again. We have reached about 0.3 millikelvin. This is almost 10 times deeper than the previous efforts, and still we are not detecting the CO in the transition 1.0. This is really, really amazing, because impose a very low upper limits in the mass of H2 to perhaps less than 10 to the 7, 10 to the 8. For this big galaxy, this is really a challenge, okay? So prospects for Argus 144, of course, that has been discussed in previous talks. Peter Barnes warns us a lot because of these side effects, but still we think that it's important to use Argus 144 for this, because we can go very fast, okay? That means that for the same amount of hours, we can reach even low sigmas, okay? For even less temperature thresholds. Okay, so I stop with the summary and conclusions, and I am open to questions. Thank you very much.
Thank you very much, Gaspar. We have a few questions in the Q&A. The first is, can quasars and supernova limit the star formation rates in these galaxies?
Yes, yes. Yeah, there are many aspects that I didn't enter in this talk. One of the feelings that the community has is that these galaxies, of course, can, I mean, the supernovae, and in particular AGN too, can prevent the formation of stars in these galaxies. In particular, for example, MALIN 1 is an active galaxy. It's a linear. It's not very active, but still there are some activity in the nucleus. And so these kind of events and radiation from a central engine can prevent stellar formation. Perhaps even many galaxies that are transiting into the Green Valley that Alberto Volatos discussed yesterday can have this kind of some sort of stellar formation truncation. And these supernovae, and in particular the AGN, are very important. It's something that is a subject of study now, sure.
How do the H1 disks compare to those in normal galaxies with extended H1, for example, NGC 628?
Yes, yes, it's similar, yeah, yeah. It's comparable in size and other peculiarities. But MALIN 1 is one of the galaxies with the faintest disk, okay? And also it's one of the biggest ones. So the amount of dark matter you can expect in this galaxy is huge. Okay, this is the dynamics of this galaxy is completely dominated by dark matter in particular, compared to other big LSBs like the one you referred.
Next question is, normal galaxies are thought to self-regulate to tumor Q values of approximately 1. Have people looked at tumor Qs in the disks of these objects, and are these disks more stable than those of normal galaxies?
Well, that is a very, very important question. In fact, with other people, we have presented a project in the national system here in Chile to investigate exactly that, this tumor number, that has not been calculated for many of these galaxies. Well, this is a personal view, but it appears that in astronomy there are a lot of fashion, okay? Many people have made very interesting discoveries, like this one by Tumbre. This is an important number that at some point, I don't know why, people has left to use that and compute that number for many things that are, for which this number is very important, okay? And for these galaxies, which are dominated by dark matter, it's very important to measure, for example, the kinematics and recompute this number. And so, yes, the answer of this question is yes, or well, it's an open question. No people has computed too much this number for these galaxies, and it's something that has to be done. Yeah.
A question specifically about your CO observations. The CO detected regions in the low metallicity galaxy WLM are very small. Could beam dilution be contributing to the lack of detection for MALIN 1?
Yes, it's a possibility. That's one of the reasons that many people is pointing to diffuse gas. Yes. Yeah. The other thing that I didn't mention too much is the conversion factor. We really don't know if the conversion factor in these galaxies is the same as the one we measure in our galaxy, for example. Yes. This is one of the fields that there are much more questions that, than the facts that we have measured. Yeah, that's why they made a very interesting target for study. Yeah.
So here's a question related to what you just said. Do you have an estimate for the metallicity of these large LSBs?
Yeah, that's another thing that's very interesting. It's like a making sentence in many literature that you read, that these galaxies have, in fact, very low metallicity, not too low. There are, in fact, the galaxies that are very low metallicity are those faint, dwarf, ultra-diffuse galaxies, or other galaxies like E-Swiggy 18, that are very low metallicity galaxies. These galaxies in particular, in general, are a little bit less than solar, okay? Samuel Boissier measured the metallicity again for MALIN 1, and it's a little bit less than solar. So in general, the galaxies I shown in this talk, including MALIN 1, are subsolar, a little bit subsolar metallicity, but not really metal poor, as we usually are used to.